Good day again, everyone. Today we'll be looking at terminal velocity. What is terminal velocity? Terminal velocity is actually defined as the velocity at which the net force of an object is zero. But how does that occur? Well, let's consider a parachuter. Now, before we begin, an important is that we will take down as a negative in terms of direction. Upon jumping out of the aircraft, experiences a downward acceleration, which we'll denote as negative g, as indicated, the negative being the downward direction. As his speed increases, air resistance, which we'll denote as drag force, we'll note it as Fd, also increases. Now, please note that air resistance force or a resistive force to air on particles that moves through it. If we draw a free diagram, we can denote or indicate that the vertically downward force weight in terms of a vector would be larger than the drag force, which acts in the opposite direction to it. Now, drag force is directly proportional to velocity, which we'll get in a bit. Now, as time increases, or eventually, the air resistance or drag force will become large enough to equal this parachuter's weight. In redrawing the diagram, we can now draw both vectors, which represent weight and drag force, to be equal in length. Now, when these two forces are equal to each other, we can say that both forces are balanced. So, what does that mean? It means that the net force acting on this parachuter equals zero. How do we arrive at that assumption? Well, if we apply a simple concept of equilibrium, one of the laws of equilibrium, where the sum of the forces acting in one direction, in this case upwards, equals the sum of the forces acting in the opposite direction, downwards. If that is applied, then if we put all forces on one side, we get zero. Our upward force being drag force, therefore, if it is allowed to minus weight, we get zero. Well, from F equal to ma, if net force equals zero, then the acceleration of this person, skydiver, parachuter, is also equal to zero. So what does that mean? If acceleration equals zero, the person neither speeds up nor does he slow down. In other words, this parachuter or skydiver will be moving at a constant velocity. This velocity, where the net force equals zero, or this constant velocity, where this net force equals zero, is known as the terminal velocity. We can denote it as v lower subscript t, at least for simplicity. But what happens if the parachuter or skydiver opens his parachute? Well, if the parachuter opens his parachute, he will experience a sudden increase in his drag force. Why is that? Well, he has just increased his surface area, so the air particles around him push upwards on this very large, now increased surface area, causing that upward force known as the drag force to increase, or that air resistive force to increase. What does that mean with acceleration? When his drag force now overcomes his weight, he accelerates upwards. So his previous descent is now slowed down. What happens next? Well, his air resistance decreases, in this case, to now balance his weight once again. The skydiver therefore reaches a new but lower terminal velocity, where both air resistance or drag force and weight are now equal to each other, making therefore, again, the net force 0. Now, let's consider for some more clarity. For a velocity time graph, as he jumps out of the airplane or aircraft, his speed increases initially. Until, of course, as mentioned, when his drag force increases to balance his weight, he therefore attains terminal velocity, which is, of course, in this case, the plateau or straight, more specifically horizontal line on the graph. At this terminal velocity, recall that both forces are equal, making the net force equal 0. What happens next is that when he opens his parachute, his speed decreases. This causes him to slow down. His air resistance decreases once again, and again the skydiver reaches terminal velocity, a lower value but terminal velocity nonetheless. How do you know this is terminal velocity? Because once again the two forces are balanced. The two opposing forces, drag force and weight, are balanced. Finally, what happens is that he reaches a low enough velocity in order to hit the ground. Now let's consider a spherical object being passed through a viscous fluid. Now viscosity is a value for the internal friction of a fluid as the body passes through it. And a fluid, just to recall, it can be either a liquid or a gas. When a body moves through a fluid, it experiences drag forces which oppose the motion of the body or object. Now, on a free body diagram as such, the spherical object experiences a weight acting vertically downwards, upthrust, which acts upwards, also known as buoyancy, or viscous force, and the drag force, which we had mentioned before. Now, drag force is equal to 6 pi r, that eta, by v, which is known as Stokes' law. What this means is that the drag force is directly proportional, once again, as mentioned before, to velocity. R is the radius of the object, the viscosity of the fluid, and v, the velocity of the object. As mentioned in the previous example with the parachuter, there comes a point where the net force equals 0 again, where some of the upward equals some of the downward forces. And this is attained by substitution, of course, our upward forces being drag force and upthrust, whereas our downward force is simply weight. In plugging these values into our equation, we will get that Fd, which is our drag force, plus upthrust minus weight equals 0. What happens at this point? Well, if this occurs, then terminal velocity of that spherical object is attained. Once again, terminal velocity is that constant velocity at which the net force acting on any object equals 0. Now, if we consider the mathematics behind each of these forces, we will get the following. Since upthrust, the buoyant force, which opposes weight in a fluid, of any object in a fluid, and can be obtained by mg, where mass is density by volume, in this case we will denote density as rho, in this case rho 1, as the density of the medium. So upthrust is obtained by the following equation. Now, volume, in this case, is the volume of a sphere. We started with a spherical object, which is 4/3 pi r cubed. Now, if we consider weight of the object, which is of course mass by gravitational field strength, In this case, mass equals again density by volume, but in order to distinguish one from the other, we will use density rho 2 as the density of the falling object. Once again, volume is 4/3 pi r cubed, and of course we get the following three equations that we can now use into our original free body diagram equation. Our objective, as we substitute the relevant value, is to obtain an equation for terminal velocity based on all the parameters that make up each of these forces. So, let's apply our mathematics. What happens if the density of the object exceeds the density of the medium? Meaning, in our case, rho 2 is greater than rho 1. Well, that would therefore make upthrust negligible. When we say it's negligible, we mean that it is so small it's not considered. Many a times, scientists say it's actually zero. In our case, it doesn't affect the movement of our spherical object. What does this mean? Well, if upthrust is no longer in play, as we can so say or indicate, that would bring us back to our original equation that we had used for our parachute, where our upward force, which in this case will be only our drag force, as before mentioned, and our downward force weight are the only two forces in play, and they oppose each other. As a result of this, we can now determine the terminal velocity of the spherical object using just these two forces. Once again, if upthrust is negligible, and this is only the case where density of the object is greater than density of the medium involved, we get the following equation. And here we can observe that our terminal velocity is directly proportional to the radius of that object squared. I hope you enjoyed the video, and if you have any questions, please feel free to leave a comment below.